Now we're going to review bonding. So major topics are covalent bonds, and we'll talk about ionic as well. When we talk about bonding, the key for any kind of bonds is that bonds form so the system can achieve the lowest energy possible. So as you see, if a bond forms, energy is really released. That's exothermic. But if we're trying to break a bond, we have to add energy. So adding energy breaks bonds. If energy is released, that means a bond has formed. For ionic bonding, we really need to understand Coulombs law. Again, we're not solving this mathematically, and it's not on the formula sheet. It just helps us to understand why some ionic compounds or some ions are more attracted to water than others. So we can use this in several contexts, but typically it's with, most commonly with the strength in ionic bonding. So the Q's are the charges. The higher the charges, the stronger the attractive force between them. And when I say higher charges, I mean like positive 2 is a higher charge than positive 1, or negative 2 is a stronger charge than negative 1. And then if the charges are all the same, then we will take one more step and look at the size of the ions. So if we have some charges are higher than others, then we don't need to worry about number 2. But if we have like sodium chloride and potassium chloride, which we're going to see on the next slide, we know that the ions that are smaller have a greater attraction to each other because they're closer together, or there's not as much distance between the ions. So ions that are closer together, and this is what we're talking about when we talk about the distance between them, in this case radius, that's a stronger attraction. You might be asked a melting point question with this, like which of these ionic compounds would you expect to melt at a higher temperature? Again, that's because it has stronger ionic bonds. Or we could even be asked a lattice energy question. If you see the word lattice energy, they're talking about the energy required to separate ions. Okay, so here's Coulombs law. So explain which salt has a higher melting point. We'll start with the first, magnesium sulfide versus sodium chloride. Again, look at your periodic table. You should think of charges. And so I'm going to lead you through how you would answer this if this is a free response question. Magnesium has a +2 charge. Sulfur is -2. You actually need to write that down. And sodium is only +1. Chloride is -1. And again, use that information to explain what you're concluding, which in this case is that MgS has stronger ionic bonding. It has stronger attraction between the ions because it has higher charges. Therefore, it would have the higher melting point. It's going to take more energy to separate those. With the NaCl and KCl, again, this is the example of we have all things that are the same charge. So, we can mention that, but that's not going to be the reason that's going to explain why we're going to pick one of these, and we should pick NaCl. If you look at the periodic table, again, these are ions. They've lost their valence electron, so we have Na plus and K plus, but we can tell sodium has to be smaller because it has one less energy level of electrons. You don't even have to go into that detail for this kind of question, but you do have to say the sodium ion is smaller or has a smaller radius than the potassium ion, or Na plus is smaller than K plus. Therefore, and here's the kicker that most kids, this is what they don't also say and don't get the credit, is the sodium ion is closer to the chloride ion. Make sure you put in the chloride ion. Therefore, it has a stronger attraction to the chloride ion. So that you have to mention that distance into the correct substance. You can't say sodium ions are closer because we're not talking about their proximity to each other. We're talking about their proximity to the negative ion they're bonded to. So again, and they could have also asked you about lattice energy, and I mentioned that at the end. We'd have the same response. The higher the melting point, the higher the lattice energy. Metallic bonding, again, notice the picture. Sometimes you have to pick out the right picture. Which picture represents ionic bonding, which picture correctly represents metallic bonding. Notice that these electrons, these red spheres are supposed to be electrons. They're all unevenly distributed. Those are supposed to be the moving electrons. So from the picture, we should be able to notice that would have to represent metallic bonds. So these moving electrons are why metals are good conductors. Here's a couple examples of alloys. Brass would be the substitutional alloy. Again, if you're asked what kind of alloy something is, look at your periodic table. If it's like two transition metals, they're going to be very similar sizes. Even if they're not in the same period, they're still going to be, unless it's just a huge difference, they're going to be in like one period under the other. They should be substitutional alloys. And interstitial alloys, when you're going to have something like a transition metal with something really small tucked into the gaps, like carbon or silicon or boron, something that is a much smaller size and a couple periods higher. Here's the covalent bonding graph. This shows you, based on the definition, that bonds form to achieve the lowest energy possible. So when you see this valley graph, always look for the lowest point. The lowest point tells you where this bond forms. That's where the most energy is released, and that's where, you can see it says too close, too far, and then this is kind of the just right. This is where you have the attractive forces offsetting those repulsive forces. And again, when we say attractive forces, we're talking about protons on one atom are attracted to electrons on the other, and protons on the other atom, it's going both ways, but then like charges always repel. So that's what that's referring to. So whatever distance where those repulsive forces are minimized and the attractive forces are maximized, whatever that distance is what we call bond length. And this number, it would be negative since it's releasing energy, but that's the bond energy. Electronegativity is the ability of an atom in a molecule to attract shared electrons to it. Like with F2, even though fluorine's the most electronegative atom, if it's bonding to itself, there's a 0 electronegativity difference, so that's going to be a nonpolar bond. So this is nonpolar. If there's and again, we're not going to actually use electronegativity numbers. I haven't really seen that in a while, where you actually you'll be given values to subtract. Sometimes they might do that, but you don't have to know the perfect range. But if there is a difference in electronegativities, and you basically have two nonmetals that you can tell aren't right next to each other on the periodic table, then you would expect that to be a polar situation, a polar molecule. But if we have a metal, nonmetal, that's when we're going to have this really great difference in electronegativity, and we would expect that to most likely be an ionic bond. And, again, we do need to know shapes. You need to know how to draw a Lewis structure. You might have to identify a shape. And again, it's, you can read through this slide, but basically everything in the atom is trying to situate itself to be as far apart from other atoms, from other lone pairs. Everything's is repelling each other. So, again, the second bulleted point, electron pairs, whether they're bonding or non-bonding, repel each other. So again, everything's oriented its stuff as far apart from each other, and that's how we achieve these shapes. So here's just a summary of the shapes. There's really two kinds of categories. We have a generic category, is what I call it. It's called electron domains. And then we have a specific shape that we call molecular geometry. So if you're asked for a molecular geometry, they want the specific shape. Electron domain is really just, it's kind of as I said, a general category, but it's counting everything around the central atom, whether it be bonding, bonds, or non-bonding pairs, or I call them lone pairs of electrons. So notice, and really if we look at, sorry, I circled the wrong thing earlier. I'm talking about electronic geometry is also called electron domain geometry. Molecular geometry is the specific shape. Notice that we have this trigonal planar electron domain geometry, which just means there are three areas around the central atom. If it's specifically trigonal planar, then those are all three bonds, three bonding pairs of electrons. But this bent is also considered generically trigonal planar electron domain because it still has three areas. It's just two are in bonding areas and one is a lone pair. But again, that's still three regions around the central atom. Again, just know the word electron domain, know that those are the general categories, but specifically know the shapes. Tetrahedral, again, here's that electron domain group. Notice it refers to, there are four regions around the central atom. If they're all bonds, it's called tetrahedral specifically. If it's three bonds in a lone pair, it's trigonal pyramidal. And if this is like water, this bent right here, two bonds and two lone pairs. Again, that's a total of four areas around the central atom, but specifically we refer to that as bent. On this slide, you do need to know some other detailed information. And I didn't mean to skip linear at the top. Notice it's in its own category by itself. This is like carbon dioxide. Carbon dioxide has two double bonds with oxygen on either side, which gives it that linear shape because carbon has no lone pairs. You should know the bond angles on this slide, and you should know the hybridization on this slide. The next slide, these get into we call these expanded valence shapes because these are elements that can have more than an octet around the central atom. So the trigonal bipyramidal group, tri plus bi gives us 5. So that's going to be some combination of 5 regions around the central atom. So if they're all bonds, it's trigonal bipyramidal. Seesaw is if we have 4 bonds and a lone pair. T-shaped, 3 bonds, 2 lone pairs, and then linear, 2 bonds and 3 lone pairs. We're going to talk about polarity in a minute. Do not say the lone pairs cause something to be polar because it's just not true, because this linear right here is completely symmetrical if you build a little model. And so even though it has 3 lone pairs, it is a non-polar molecule. So again, I always try to say that because kids see a lot of lone pairs and molecules tend to be polar, but that's not always the case. So don't make that association, and again, we'll go over that is not the reason. You do not need to know these bond angles. Don't worry about hybridization. You just need to know these shapes. And then the last few shapes, octahedral. If you build this model, the reason it's called octahedral is it doesn't have 8 bonds. It's really, if it's all bonds, it's 6 total bonds or 6 regions around the central atom. But if you build an octahedral molecular geometry shape, it has 8 faces. So that's where that is coming from, because this, is a 3-dimensional model. So 6 total bonds is octahedral. Square pyramidal is where you have 5 bonds in a lone pair. Square planar, again, this is an example of a shape that has lone pairs and is a completely symmetrical molecule and therefore is nonpolar. Square planar, 4 bonds, 2 lone pairs. Don't worry about the bond angles, know the specific shapes. Here is a slide just to help you understand polarity. Polarity of molecules is all about their shape. So carbon dioxide, even though the carbon-oxygen bond is polar, notice there's a dipole arrow drawn and you can see the electronegativity difference. Again, you don't need to memorize numbers like that. But because of the shape, these dipoles are both pointing in opposite directions, which means they cancel. So carbon dioxide, due to its linear shape, has, the dipoles are canceling. It is nonpolar. However, with water, the lone pairs aren't drawn here on the oxygen, but because of the lone pairs and the 2 bonded atoms, it is asymmetrical. The shape being bent causes this to have an overall dipole, so it is a polar molecule. And you can tell from the shading on those space-filling models below. Here are some other examples. If we have a 2-atom molecule like HCl, you should assume it's polar. Again, you're not going to have the electronegativity numbers, but unless it's right in the same period with the atom next to it, again, those would have very similar electronegativities. So if there's any separation, it's going to be polar. Trigonal planar, notice BF3 boron can only have 3 bonds. It only has 3 valence electrons. It's going to be nonpolar. All those dipoles cancel. Carbon tetrachloride, tetrahedral, all the dipoles cancel. Ammonia has the lone pair that gives it that trigonal pyramidal shape, and so it's definitely going to be polar. It has a net dipole. And even tetrahedral here, if you don't have the same atom bonded all the way around, there's going to be a difference in electronegativities, and you would expect that to be a polar molecule. So here's how you explain polarity. You need to state the shape and tell what that shape is going to cause the dipoles to do. So I just used 2 common examples. Water is polar, has a bent shape, which causes it to have a net dipole, which means it's polar. Another way to say net dipole is overall dipole moment. That was printed on the previous slide. And then if we look at carbon dioxide, which we saw earlier, carbon dioxide is nonpolar due to its linear shape, causing the dipoles to cancel, or has an overall dipole moment of 0. So if you see that term, if it has a dipole moment, it's polar. If it has a 0 dipole moment, it is nonpolar. Just to make sure you understand the relationship between bond characteristics, short bonds are stronger. It pulls the atoms closer together. And have higher bond energy, meaning a stronger bond is going to take more energy to be added to separate or to break the bond. So if it takes more energy to break a strong bond, that means when a really strong bond forms, it's going to release a lot of energy because it works both ways. In this table, the graph below, the strongest, shortest bond of nitrogen is the triple bond, as you can see, and the weakest, longest bond would be the nitrogen-nitrogen single bond. Here's the bond energy relationship for delta H. Again, I wanted to include this. It's in the enthalpy unit as well because, we're drawing Lewis structures. If you see this table right here, you need to draw Lewis structure. It's showing you the bond energies. You need to verify that you know how many bonds are in the molecules. The reactants are where you're going to break the bonds. Count up how many bonds that would be broken. Use that value that goes with it. So you're going to sum up all the bonds and the reactants that are going to be broken. Don't forget your coefficients minus the sum of all the new bonds that are going to form, because that's going to release energy. So once we have this total, if it's overall negative, we know it's overall an exothermic process. If it's overall positive, we know it's overall endothermic. So again, watch your coefficients, make sure you draw your structures. Sometimes when we draw a Lewis structure, you'll realize, like with this nitrate ion here, that there's 3 oxygens and one of them happens to need a double bond so that we can, share enough electrons. Because again, when you draw these Lewis structures, I hope you're adding up your valence electrons so you'll know when you've used them all or not. But when you realize that there's a double bond that could be drawn correctly in more than one places, you have to draw all of them. This is showing resonance because there's really more than one way to draw this, and really none of these structures is correct. Notice there are these double-headed arrows, and what those double-headed arrows mean is that not one of these structures is correct. It's really an average of all 3. So how do you average a double bond and 2 single bonds? I've tried to show you here. It's just there are 4 total bonds, 2 in the double bond, 3, 4, divided over 3 locations. So as an average, that's a 1.33 bond, or a 1 1/3 bond. A 1 1/3 bond is a little bit shorter and stronger than a single NO bond, but if we were comparing it to a double NO bond, that would be a stronger connection. And non-bonding pairs and bond angle, these are some of the simpler shapes. This is in the tetrahedral electron domain category. So we have specifically tetrahedral, trigonal, pyramidal, and bent for water. You might be asked a bond angle here. You really do need to know these specific numbers. So tetrahedral, when you draw it flat on a piece of paper, it looks 90 degrees. Make sure you realize three-dimensionally it's 109.5. When you compare that to the bond angle in ammonia and H3, the bond angle is a little bit less. And the reason is right here, non-bonding pairs. That lone pair on nitrogen is physically taking up a little bit more room and space, and it's repelling the bonded atoms and pushing them a little closer together. So the bond angle goes 109.5, a little bit less, 107, and then once you get to water, since it has two lone pairs, it has two lone pairs that are taking up more room and space, so they're repelling each other and repelling the bonded atoms and compressing that angle a little bit more to 104.5. So 109.5, 107, 104.5. When these questions have been on the exam, you could be within, they gave a range of values. So like if for tetrahedral, if you were between 109 and 110, like if you just said 109, you got credit. For this one, I haven't seen that on there in a while, but it needs to be around 107 and 104. So if you really could just remember 109, 107, 104, you should be in good shape. And then formal charge. You might be asked, there'll be two Lewis structures for a drawing, and you'll ask which one is the best structure. You want to choose the one that has formal charges closest to 0. And this kind of goes through the math to do that. It's almost, and you can read that on your own, it's almost easier to see this with an example. You're basically comparing the number of valence electrons each atom has compared to how the electrons are distributed or assigned to it in the structure itself. So if we look at this example, we know carbon dioxide should be drawn with two double bonds, but this is just a good example to see why we're drawing it that way instead of doing a single and a triple. So if you notice, this first line of valence electrons is going to be the same all the way across because those are the valence electrons that oxygen and carbon have if we look at their group number on the periodic table. Minus, and the next thing is how many electrons are assigned to that individual atom. And so really what you have to do is, for this oxygen, I'm going to count the two lone pairs, so that's 4 from the two lone pairs, but each bond, notice there's a line drawn down the middle. Each of those bonds, you think about it as the oxygen contributes an electron to a bond, and so does the carbon. So if there are two bonds, oxygen's contributed 2 electrons. So that's where they're getting 6. 2 from the lone pairs and 1 from each bond. Carbon has 4 bonds around it, so it's contributed 1 electron to each of the 4 bonds. And then this oxygen is identical. So 6 minus 6 is 0. They're just subtracting down the column. That's how we got the formal charges of 0. So we can tell these zeros are telling this is a very stable structure. Now on this other side, we have 646 for the valence electrons, but notice this oxygen has 6 electrons coming from those lone pairs plus that bond, so that's where that 7th electron's coming from. So 6 minus 7 is -1. The carbon is the same in the middle since it still has 4 bonds. They're just distributed a little differently. It doesn't really matter. But then this oxygen, since it has 1 lone pair and then a triple bond, that's 2 plus 1 electron from each bond of 3, so that's 5 total. 6 minus 5 is +1. So again, you're looking for the structure that has the formal charges closest to 0, and that's the best structure. The last thing are sigma and pi bonds. If you're asked how many sigma bonds are in a molecule, that means count up every single bond you see. Every single bond is a sigma bond. And if there's a multiple bond, so here's a double bond, here's a triple bond, one part of a multiple bond is a sigma bond, and the rest of it are pi bonds. So if it's a double bond, it's 1 of each, 1 sigma, 1 pi. If it's a triple bond, 1 sigma, 2 pi. When you take organic chemistry in college, you'll learn lots more about this. It's a little bit more complicated than this implies, but you still need to realize sigma bonds are single bonds and one part of a multiple bond. Pi bonding you would only find in a double or triple bond.